This lecture will be about a special probability density function, the normal probability density function. Okay, before we talk about the normal distribution function, we need to talk a little bit more about how probability density functions work when they're continuous. For example, what's the cumulative distribution function look like? Well, the cumulative distribution function is the probability that x is going to be less than or equal to some c. In other words, the probability of the interval from minus infinity to c, like in the picture when c equals 1. If we write down this integral from minus infinity to c of f of t dt, we know from our previous chapter's experience that there is an antiderivative and that this function capital F of c minus capital F of minus infinity, okay, is going to give us the area under the curves. But what is capital F of minus infinity? Well, if you look at the graph in front of you, cumulative distribution functions always end up being 0 at minus infinity. When we take the limit as x gets large without bound in the negative direction, and this is because the probability density function has to have horizontal asymptotes of 0 in order for this to work. In order for the area under the curve to be a finite number, the tails, the two ends, have to have horizontal asymptotes at 0. Now, as we have seen, it might actually drop off and be 0 from some point on. Okay, but in the case of the normal distribution or many cumulative distribution functions such as the one in the graph in front of you, it's a horizontal asymptote. Well, since we have 0 for the last term in the first line, that means that the probability that x is less than or equal to c is the cumulative distribution function f of c. So the fundamental theorem of calculus tells us that the derivative of the cumulative distribution function is the probability density function. Moreover, what is the probability of a point? When dealing with a continuous probability density function, one must always work with outcomes that are intervals. The probability that a specific event will occur would be the probability that x is both less than or equal to and greater than or equal to a constant. That would be the integral from c to c of f of t dt, which would be the cumulative distribution function at c minus the cumulative distribution function at c. Well, that would give us 0. The integral under a point, the area of a vertical line with no width, is 0. This is completely different from the discrete probability density function. Remember, the discrete probability density function using a fair six-sided die and calculating the probability of obtaining a 2 on the top face would be the probability that x was equal to. In other words, it was greater than or equal to 2 and less than or equal to 2. And this, remember, is 1/6. So, the normal probability density function, or the density function whose cumulative distribution function is the normal distribution, or what is commonly referred to as the bell curve, is one of the most important continuous probability functions. This is going to get used in lots and lots of applications and may very well be the focus of an entire course. But the definition is not simple. The normal probability function with mean mu and standard deviation sigma, notice these are Greek letters, is given by the probability of x is 1 over sigma times the square root of 2 pi times e to the quantity x minus mu squared divided by the quantity 2 sigma squared. That was a mouthful. So the probability that x lies in the interval from c to d is the probability that c is less than or equal to x is less than or equal to d, and that would be the integral of the probability density function you see. Let's take a look at that. The normal distribution function would be the integral from minus infinity to t of 1 over sigma times the square root of 2 pi times e to the minus quantity x minus mu quantity squared over the quantity 2 sigma squared dx. Oh my goodness. In the graph on the left, we see the normal probability density function. And as the graph is labeled, the area under that curve is indeed 1. it is not a trivial matter to show that that area is 1 and requires tools that have not been covered yet in this course. Moreover, the normal cumulative distribution function would be the area under the curve from minus infinity to t. In the picture, t is 1. And that area is also not easy to compute. In fact, we have no methods that we know of for computing e to the minus u squared du. So, we are forced to use our calculator. Let's work through an example together. For the normal probability function with mean mu equals 0 and standard deviation sigma equal 1, use a calculator to find the probability that negative 1 is less than or equal to x is less than 1. Now, we can write out that the probability that the event occurs in the interval from minus 1 to 1 is equal to, let's see, we have 1 divided by sigma times the square root of 2 pi. And sigma is a 1, so we can leave this off. Times the integral from minus 1 to 1 of e to the minus x minus mu, that would be x squared over sigma squared times 2 dx, like so. But we don't have any techniques for calculating this value without the help of a calculator. Now, I know for a fact that the TI-84 Plus has a function for calculating the normal distribution. We would write normal. You would need to look in the math functions for normal CDF for cumulative distribution function, and you will want to go from minus 1 to 1, and your mean will be 0 and sigma will be 1, and that this will give you the right value, 0.6827. However, there are no steps to show you. You are going to have to use a calculator, and you're going to have to familiarize yourself with the functions that you need to use on your particular calculator to make this work. I could show you how to do this online using Wolfram Alpha or a number of other online tools. However, for your final, you will need to use a non-graphing calculator, such as a TI-84 Plus or some other more advanced Texas Instruments calculator with no graphing capability. Now, to work this problem on your own, you must have already obtained a calculator and figured out how to use it in order to obtain the answer using the normal distribution function capabilities in the calculator of your choice. So, for the normal probability density function with mean mu equals 0 and standard deviation sigma equal 1, use a calculator to compute the probability that negative 2 is less than or equal to x is less than or equal to 2. Will this be 0.6827, 0.9545, 0.9973, 1.00, or none of these? Thank you.